So today we'll complete the slow bond that we've been seeing for the last two lectures. Just to recap, the way we were doing the slow bond was in like three stages. Sorry, this should be just a typo. There's the first stage, which is the first m minus order square root m bits of communication, and then the second stage, which is like the remainder of the communication, and then in the middle we do some kind of cleanup. Okay, so today we'll do the cleanup and the second stage. We built a bunch of facts and tools towards this. So first thing was that in the first stage we found a transcript such that there is this carefully chosen set of inputs SPI associated with it, which is a subset of all possible inputs that can be given to both Alice and Bob that reaches this node. Right? It's not exactly this set, but it's a carefully chosen subset, and we discussed in detail how to choose this, etc. And we visualize the subset as a two-stage set. So every element here is like a tuple. The first part is a matrix and the second part is a vector. And so we want to think of this as set x pi, which is a set of matrices associated with this set x pi. So these are all x such that there exists some vector a, so that this tuple is an s pi. Yes, and then for every x and x pi, we associated this set ax, this capital X, not curly x. So this is for this particular matrix to be all the vectors a such that xa is an s pi. So remember we equivalently saw this as some kind of tree. So you had like epsilon, then you have this matrices x, and all these so these matrices had a bunch of vectors associated with them, etc., etc. So this set is the set x pi of matrices, and for any x, the set of children, so the vectors is a set a pi, sorry, ax, not curly x, it's with a particular matrix x. And the way we chose these inputs and this transcript was that there was sufficient number of matrices and there was sufficient number of vectors associated with it, each matrix. So we had these two properties, that cardinality of x pi was at least, so what's the maximum cardinality? So it's the x root, the set of inputs at the root, which is set of all m by n matrices, 2 to the mn divided by 2 to the m minus order square root m. So this said that like the number of matrices decreased by half for every bit of communication. So every bit of communication leaks something like 1 bit of information on the matrices. And we also had this very strong guarantee that for all, so no matter what x you condition on, so for all x and x pi, this set a x was also of large cardinality. This is, so the maximum possible set of vectors that you can associate is the maximum number of m bit vectors, so that is 2 to the m, but this was at least 2 to the m by 2 to the m minus order square root m. So you had something like 2 to the order square root m vectors associated with each matrix. Okay, so this is what we had, and now we wanted to do this cleanup where we wanted to do two things. So in the first part of the cleanup, we want to identify revealed rows. So these are rows where players have learned more than tau bits of information. Oops, I have. So this recording menu is visible. Sorry about that. Guess it's gone now. Bits of information. And then for every such row, like if we identify that some row I is revealed, this implies that we want to make sure that this row cannot be used in the second stage because they've already learned too much information. And to enforce that this cannot be used in the second stage, we want to set that AI is equal to BI for every vector that we are considering. Okay, so we won't make it explicit, but we'll see what to do. So So in particular, what we want to do is select for every x that we kind of choose after identifying the revealed rows. We want to, in the set curly ax, we want to set ai equal to bi for everything. So we want to do this, and then we want to say that the number of such revealed rows is at most the communication divided by the threshold. Okay, and at the end we want to keep promise 1. So keep promise 1. And what do I mean by that? For every vector x that survives all this cleanup process, we want to choose some vectors a and b such that a is not equal to b. So I'm not going to make this super explicit, but we'll see what it is. But so it's guaranteed. Second stage. Okay. So to identify revealed rows, we needed some kind of measure of information, and we came up with this measure, which let me just quickly jog your memory. This was this notion of average degree. So given a set X, which is a subset of matrices, so not necessarily m by n matrices, so it could be like, I don't know. So what are we going to do? We are going to identify revealed rows one by one. So we might be looking at partial matrices. We might not look at all the m rows. So this is the general definition. This is for like, so given any p by q matrix. So this is not necessarily m by n. What are we going to do? So for any row I, we defined average degree of that row in this set X to be the cardinality of the set X divided by cardinality of X minus I, which, if you remember, is all the matrices that you get by removing the ith row. So the INP ith row from this matrix. And we thought of this as this kind of bipartite graph where we had on the left side we had all the matrices. So the picture is not up to scale. Left side is going to be much larger than the right side. Side has matrices with the ith row removed. So these are like sort of partial matrices. So every node is some kind of partial matrix where there's a gap in the ith row. And on the right hand side you have uh, all the matrices of the set X projected only onto the ith row. So these are just one rows. So this is just the ith row. So this is like conceptually this is the ith row. This is everything but ith row. Everything else. And there's an edge between these two nodes if the completed matrix, by which I mean that you take the right hand side row and put it in the put it as the ith row of the partial matrix on the right hand side. If that completed matrix is in the set X, then this is a edge, right? And the completed matrix is in this thing, okay? And we saw that like when like no information, so if you take X to be the entire set of matrices, when no information is revealed, the average degree is something like the maximum possible. So if X is 0 1 to the p by q, then in fact for all I in p, it is the case that average degree of I of X is 2 to the q, because there are q columns and then there are 2 to the q ways to fill them, and all of them are possible because are the set of matrices the entire set of matrices. So this is the maximum situation where the players have learned nothing about a row. So this is so logarithm of this is q. So there are q bits of information in a row, and this tells you that they haven't learned anything. And if they have learned, so by our definition, a row is revealed if the players have learned at least tau bits of information. So a revealed row in this measure of information would correspond to the following. A revealed row is where they have learned at least tau bits of information. So the average degree should have dropped by a factor of tau, but we are measuring information in bits, so that's like logarithm of that drop should be tau. So claim that this average degree, so these are rows I such that average degree I of that row is at more is strictly smaller than 2 to the q minus tau. So for example, so if we set tau to be 1, so that's like, so tau equal to 1 implies rows where they know 1 bit of information, right? And by this definition, so this is equivalent to uh, rows where rows I such that average degree of I in X is at most 2 to the q minus 1, right? Sorry, this is strictly smaller than 2 to the q minus 1. And if you take the logarithm, that's like it's saying that the amount of information left unrevealed in that row is like q minus 1 bits. So it's like saying, okay, they have learned 1 bit of information. Yeah, I hope this definition is intuitive enough for you. Are there any questions about this definition of information? This should be a good time to ask, because the rest of the proof is just proving some properties for this definition and then completing the proof. Okay. So if there are any questions, please stop me. So I'll continue with the properties that we want to prove for this definition of information. Or rather, so the first one we want to say is that, okay, suppose we have a set X, which is, so this is this property that we wanted, that if p bits is known about the set of matrices X, X pi, so this would be equivalent to saying that X pi is at least is something like roughly, it's roughly 2 to the maximum possible divided by 2 to the t. So this is like, okay, so what I'm saying is that exactly t bits would be known, at least t bits would be known if then cardinality of X pi is at least this much. We'd assume that it's exactly this much or roughly equal to this much. So if t bits of information is known about the set of matrices, then these t bits should be then these t bits should be spread across the rows. So this is the informal property that we want to prove. Formally, what we are going to say is that, okay, so for any X which is a subset of m by n matrices such that this condition is there, that x is at least something like 2 to the mn minus t, yeah, then there exists a set of rows so okay, so maybe it's better to start over in the next page. I can't complete here. Okay, so this is theorem 1. So for any set X of matrices M X, where there hasn't been too much information that is revealed about X, so that's saying that X is at least some cardinality of the total number of matrices, it's at least this much, then there exists row is a subset of rows, so these are rows like revealed rows, such that if you so one thing is like how many revealed rows should be there. So one thing is that row should be at most. So can someone take a guess? So the amount of information known about the matrices is T, and we set a threshold for the revealed rows. Oh, sorry. So I should also have this parameter threshold 3, and for any tau, which is like a natural number, assume that tau is it is non-zero. It's a natural number which is not zero. There exists a set of revealed rows denoted by rho, such that this cardinality of these revealed rows. So maybe I would not use small t for this. Let's use t. So t corresponds to amount of communication. So this should be at most t by this tau. So t is the total number of information that's revealed on the set of matrices, and tau is a chosen threshold. So the number of revealed rows should be bounded by t by tau. So this is one property, and we want to show that. So this says that number of revealed rows is bounded, and the other fact we want to say is that, okay, apart from the revealed rows, there are no, like, everything else is unrevealed. So on every other row, the players know at most tau bits of information. They know strictly less than tau bits of information. Okay, so what is this property saying? So this is saying that if you take x and project away the rows indexed by this revealed rows, so if you take the set of matrices x and remove all the revealed rows, so for x row, there does not exist. So, or indeed, like if you say in the other way, for all j, so for all rows of this set of partial matrices, so these rows come from the set of rows in the original matrix minus the revealed rows. So for all j in m minus rho, the average degree j of this x minus rho is strictly greater than 2 to the, or strictly greater than or equal to 2 to the n minus tau. So remember that the maximum amount of information that's there in the row is like n bits. That corresponds to average degree being 2 to the n, and the average degree being at least 2 to the n minus tau says that the players know at most tau bits of information. So this says that, okay, row is the set of revealed rows. So it satisfies two conditions. One condition is that the number of such revealed rows is bounded by the total communication divided by the threshold of information that we are setting for each row. And if you project away the revealed rows, every other row has high average degree. Okay, so in that set, okay, it's not, so there's a subtlety here. So you have to note that this is not average degree in the set X. It's average degree in the set of partial matrices where you have removed all the rows indexed by this row. Okay, because we did have one example where uh, all the rows had low average degree if you looked at the original set, but then there's a way you could, like, if you remove one of the rows, then it is possible to bring the average degree to the maximum possible. So this was this example where the players, so if you remember, we had this example where the set X was the set of all matrices whose every column has parity 0. So in this example, if you remember, if you look at the average degree of any row, it was just 1, because what's the case here? So if you look at, for any I, if you look at x minus I, that gives you some matrix with the ith row missing, and the average degree of, so if you take a particular x minus I, the average degree of this, the degree of this particular x minus I to xi is just 1, because once you have this partial matrix and you have filled in all these values, let's say 1 0 0 0, then you know, because the parities of every column has to be 0, then you completely know what this row is going to be. So there's exactly one edge going from this to this. So, and this is independent of every what row you choose. So it's impossible to get this condition for the larger set. So this condition that they don't know too much information on the unrevealed rows is impossible to attain if you look at the set of all matrices, but it is possible to do this once you remove the revealed rows. But how do you remove the revealed rows? It is something that we have to decide. And yeah, also the other thing is that again, yeah, and there is some more subtlety with ensuring that all the AIs are equal to PI, but then that's not part of this theorem. This is, let's try and prove this theorem. Are there any questions at this point? Okay. Okay, if not, let's prove this theorem. So how are we going to do this? Uh, what we are going to do is, like, we will do a kind of pruning algorithm. We'll prune the set of matrices un, until there is a revealed row, and if there are no revealed rows, we stop. So this is what we're going to do. So we start with the matrix X. So this is the pruning algorithm. So the task of this algorithm is to identify revealed rows and then output those revealed rows, and then we'll prove that the number of the revealed rows output by this algorithm satisfies all the properties claimed by this theorem. Okay, so initially the revealed rows is set to be empty, so row corresponds to revealed rows. And remember, there's this threshold tau. It's the threshold. We somehow know this. So this is what we're going to do. So while there exists some I, there is a row which is outside the set of revealed rows. So it's the set of rows is this. So these are the set of rows, right? These are the rows, and these are the currently identified revealed rows. Yeah. So while there exists an I, which is a revealed row. So what is the definition of a revealed row? It says that in the current set, the average degree of this row is quite low. And how low? While there exists an I such that average degree of this row with respect to the set of matrices where the currently identified set of revealed rows are removed. So that is X minus rho. So remember, rho is a subset of M, and so this X minus M meant that so X is a collection of M by N matrices, and you remove every row that is in this row. Okay, so there's some confusion with the word row and the letter row. Maybe I should have used something else here. So for clarity, let me just make this I. So I is going to be the set of revealed rows. So then, oops. So there's one more modification. This should be I, and this should also be I. Yeah, so sorry for the somewhat bad notation. It's when I say this out, I realize that there's a confusion between row and the set row. So I is a set of revealed rows. So we look at the average degree inside this set. So if you remember in the last class, we described how to do this. Like you, on the left hand side, you look at every partial matrix from here and remove I. So that would be like a matrix from the set X where the in set of rows indexed by capital I as well as small I are removed, and on the right hand side you just have the ith row. Okay, such that average degree, so this is revealed. So what's the threshold on average degree? This should be strictly smaller than 2 to the n minus t. So this says that there is more than tau bits of information known. If at most tau bits of information were known, average degree would be quite high. It would be at least 2 to the n minus tau. So here we are saying that, oh, it's not, it's strictly smaller than that. So then what do we do? So what should we do? This is definitely a revealed row. So we are going to add I to the current set of revealed rows. So I becomes I union I, and then we continue. So like, yeah, repeat until this happens. So at the end, and while we are going to output I. And I claim that I would satisfy these properties. Yeah. So what are the properties I is supposed to satisfy? Let me update every row by I here as well. So this is, there exists some I, this is I, this is minus I, this is minus I. Let me know if I miss some row. Oh yeah, see one more. Yeah, so these are the two things that we need to show. So it's sort of clear. The second property is obvious, right? So if you call this like, so this property says that in x minus I, there are no more revealed rows. So everything should have average degree greater than 2 to the n minus tau. That's obvious, right? Because if our algorithm ever stops, it's clear that there is no such j. Because if there is, we will continue. Yeah. So the proof of theorem 1, I think I called it. Okay, I didn't call it theorem. Okay, I did call it. So proof of theorem 1. So let me call this property 1 and property 2. So if the algorithm stops, if the above algorithm stops, property 2 is trivially true. Yes, but maybe we'll run this algorithm forever, but we will prove that it is not the case by proving property 1. So property 1 shows that if you have some guarantees on the cardinality of x, or which is in turn related to how much information the players know about the set of the set of matrices that we are considering, if you have this guarantee, then the number of revealed rows is the communication divided by the threshold. So after these many steps, our algorithm should stop, because in every step of the algorithm we are increasing the cardinality of I by 1, exactly 1, right? So if we prove property 1, then we get that cardinality of I is at most t by tau, and hence the algorithm has to stop as long as t by tau is smaller than m. Yeah. So we'll just end up proving that. So how do we prove property 2? This is also not too hard. So, sorry. Yep. So property 1 I called. So this says that cardinality of I, the number of revealed rows at the end of the termination of the algorithm, is at most this t by tau. So t was the communication and this was the threshold. So how do we do that? So we're going to do that by proving the following invariant. So we prove the following invariant. So invariant for the while loop. Okay, so for every execution of the while, every run of the while loop, we'll maintain the following. And then the invariant is going to be that if you look at the cardinality of x minus I versus the maximum possible set of such partial matrices. So this is some calculation that we have to do. So how many matrices are how many m by so versus the cardinality of the universe, the maximum possible universe. So x minus I was what? X minus I is a set of, it's a set of m minus I cross n matrices, right? So these are binary matrices where there is So how many rows are there? So the number of rows is cardinality of m minus I, which is nothing but m minus cardinality of I, and the number of columns is n. So how many possible binary matrices are there of this form? That is exactly equal to, so you have m minus cardinality I rows and then n columns. So this is, so we want to understand, so X is not a perfect set of matrices, right? The players have learned some amount of information on the set of all matrices, and from that subset we are projecting some rows away, and we want to know how much information is there in these rows relative to the maximum possible, right? We were always measuring amount of information with respect to the maximum possible universe. So we said that we knew at most tau bits of information here, because this cardinality of X is at least 2 to the minus t of the cardinality of the universe. So this is the, so if I take this thing, so this is the cardinality of the universe set, and this is saying that the cardinality of X is at least 2 to the minus t. So if you normalize with respect to the universe, that's like, that's how much information is like the relative to some scaling. So you'll need to take some logarithms and do some scaling, but intuitively that's the amount of information. So we're going to maintain the following invariant. So I'm going to erase this calculation. I hope you understood this calculation. So X minus I are matrices where there are m minus cardinality I rows and n columns. So the maximum possible number of them is just 2 to the m minus I times n. This thing n is at least going to be yes, 2 to the, so this one I'll need to normalize, not really, yeah. So yes, so I'll say that this would be at least 2 to the t, yes, it's at least minus 2 to the t. Um, 2 to the minus t, I think I'll need a yes, yes. So this is at least going to be the so this t is the amount. Okay, so this is the, so just trying to figure out the normalization. So this is what we want to know, right? We want to say that like p bits of information is there in the set of matrices, and we have identified cardinality I revealed rows, so they should intuitively corresponds to tau bits of information each. So this should be at most, so the remaining information and this set should be at most this much. Yeah, so they're saying that this is at least this much. Okay, so this is t is the total number of information. So this total information in X, right? And for every revealed row, we know that there is at least tau bits of information. So the amount of information left in the set of matrices where you remove these I rows should not be t, right? When, if you intuitively believe that this measure of information is going to work, whenever we identified whenever we identify a revealed row, that should account for at least tau bits of information. And when we have identified cardinality I many such revealed rows, so it of this amount information should be taken away from the current set of matrices. So because we are projecting those rows away, so the amount of information that is there in this matrix initially was 2 to the minus t, so it was 2 to the minus t of the universe, and now it should come down by this at least it factor. So this at least 2 to the minus t minus it. So if that didn't make total sense to you, but at least understand this intuitive calculation. This is like the number of revealed rows cross threshold. So this much information, so this was the total information, so this much information must be taken away by projecting those rows away. So this is, yeah, this is the intuition. And why is this invariant enough? I say that if we prove this invariant, we are done. Can someone tell me, like, what can someone give me an upper bound for this value? So we don't know what is x minus I. This could be small or large. We knew that x is at least 2 to the minus t, but 2 to the minus t of the total universe. But once you project some rows away, we don't know what happens. But in the worst case, this cannot be bigger than this one, right? The numerator is at most the denominator, because the denominator is the universe from which the numerator comes in. So this ratio can be at most be 1. Another way to write 1 is like 2 to the 0, right? So this says that 0, so this is equivalent to saying that 0 is at least minus t minus I tau. So if you take the minus, this is like saying that, so if multiply by minus, everything should, the side of the equality should flip, or you take minus t to the other side, whatever. So this would tell you that t is at least I tau, and this implies that t by tau is an upper bound on I. So if we maintain this invariant, then we are done. We prove property 1. Is that clear to everyone? Are there any questions at this point? Okay, so if not, let me continue. So we want to prove this invariant. We want to prove that every run of the while loop would maintain this invariant. So this part, so every such thing like this run would maintain invariant. So this has invariant, maintains invariant. How do we prove this? So one way, so the number of runs of this while loop is synonymous with the cardinality of I, right? If cardinality of I is 1, that means this while loop ran for 1 time. Cardinality is 2, it ran for 2 times, so on and so forth. So one good way to prove this invariant would be by induction on the number of times the while loop is run, which is equivalent to saying do this by induction on cardinality I. So this is some kind of a potential argument. If you have seen information theory before, this is like a standard potential argument, or even some crazy data structure. So this is the proof of the invariant. So, and this is done by induction on I, cardinality I, not the actual set, but the cardinality. So initially, before the loop is run, what is I? I is 0, because I was set to the empty set. There are no revealed rows. And we want to prove that. So what is the invariant? Okay, so maybe before I prove this, just let me write down the invariant somewhere very quickly. So the invariant was that cardinality of x minus I as measured with respect to the total number of such matrices is at least 2 to the minus t minus I times tau. Yeah. So when I equal to 0, what is this invariant? So this is saying that what is x minus I? X minus I is just x minus the empty set, which is just x, right? This is saying that cardinality of x divided by 2 to the mn, because I is 0, cardinality I is 0, the denominator would be 0. This is at least 2 to the minus t. And this I tau is 0 no matter what tau is, right? And this is something we had made as an assumption in the theorem, in the statement of the theorem. So this is just by the statement of the theorem. This is, let me just write this, by assumption in the statement of the theorem. So this was indeed saying that we know at most like t bits of information about a set of matrices. So if you remember, yeah, just this, the statement had this. Oops, sorry, I went too fast. There's some refresh issue. So the statement said this thing. So this highlighted thing, right? That cardinality of x is at least 2 to the mn minus tau, and this is what we are claiming. This is what the invariant at I equal to 0 says, right? So this is clear. So by the assumption that at most t bits, capital T bits are known, we know that this is true. So this is just by assumption. And now we need, it's the crucial induction step. So this is the induction step. So induction step. So we are considering the following thing. So we had, so at the beginning, so before the current run of the while loop, we had this set I was the set of revealed rows, and the while loop identified some revealed row j. So I think I called it I, but yeah, so I called it I, but let's call this j. I hope that's the only update I have to do. Didn't call it I anywhere else. Oh yeah, so this should be average degree of j. Yeah. Yes. So what does so identified j, and what happens? I becomes I union j. So at the beginning, by induction, we know that the invariant is true at the in by induction. So we know that cardinality of x minus I. So there's like two i's here. So maybe I'll call this I1 and let's call this I2. So at the beginning of, so I1 is the set of revealed rows at the beginning of the loop. So by induction, we have proved that already, that it maintains the invariant. So this with respect to 2 to the mn minus, sorry, it's easier, 2 to the m minus I1 times n is at least 2 to the t minus I1 times tau, 2 to the minus t. So this is by induction. And now we want to understand, we want to prove the invariant. So we want to understand what happens when you add j to I1. So what happens? So what is x cardinality of x minus I? So x minus I2 with respect to cardinality of x minus I1. So this is a major thing that we have to solve. If we have to somehow use the invariant, then we have to like find a relation between x minus I1 and x minus I2, and then we can maybe plug in something from the invariant for the last step and then do something. So here is what is important. So we know that I1, sorry, I1, j was a revealed row. So what does it mean? So this says that, so if you look at this graph where you have x minus I1, and from the set of matrices you remove the jth row that you have on the left side, and on the other side you have x minus I1, and you have just the jth row on the right side. So the average degree, so for j to be a revealed row, what's the average degree of a node here on the left side? So the average degree here was, so average degree j of x minus I1 was at most 2 to the n minus tau, right? So this was quite low. And what is x minus I2? So since I2 is just I1 union j, so this x minus I2 are the set of all matrices where the rows I1 and rows j are both removed. And what's that? That's exactly this left side. So this is also equal to x minus I2, right? Because I2 is just I1 union J. So this is just the cardinality of the left hand side. So what are we trying to understand here? We have this bipartite graph. We know that the average degree on the left side was quite low. We want to estimate the number of nodes on the left side. And do we know what's the number of edges? So what's the number of edges here? So the number of edges here in this graph, what is it? It's by definition. So there's an edge between these two partial matrices if the completed matrix is in x minus I1. So this is exactly equal to cardinality of x minus I1, right? Right? And by definition of average degree, this is saying, what was the definition of average degree? It is the number of edges divided by the cardinality of the left side. So average degree is nothing but x minus I1, cardinality of x minus I1, which is the number of edges, divided by the cardinality of number of left side vertices, which is x minus I2, because of the fact highlighted in blue. Yes. So what does it tell you? Like, this tells us that x minus I1 is not too large compared to x minus I2. So what did we get? So if you like simplify this, so average degree J of x minus I1. So sometimes I might forget writing a minus. So if you see any mistakes, please let me know. Do tend to make these mistakes. So this is at most 2 to the, sorry, strictly less than 2 to the n minus tau, and this by definition is cardinality of x minus I1 divided by cardinality of x minus I2. There's a minus here. So this implies that cardinality of x minus I1 minus I1 is at most 2 to the n minus t, cardinality of x minus I2. I mean, this is also a simple fact to say, right? I mean, every node here has degree at most, like on average it has like degree 2 to the n minus tau. So the total number of edges cannot be more than the left side times the average degree. So this is another way of saying that total, so this is like number of edges is just bounded by average degree times cardinality of left side. If you wanted to put some more intuition into that calculation. So we have this. So now we are trying to prove the invariant, right? So what are we trying to understand? So we are trying to understand what is x minus I2, cardinality of x minus I2 with respect to 2 to the m minus cardinality of I2 times n. So by this we know that the cardinality of x minus x2 is at least this divided by this. So this is at least cardinality of x minus I1 divided by 2 to the n minus tau, 2 to the m minus I2 times n. Yeah, I just plugged in the equation that we wrote earlier. So we know that x minus I2 is at least, it cannot shrink by more than 2 to the n minus t factor by the above calculation. Yes. Now we can use the invariant about x minus I1, but x minus I1 was its normalization was with respect to its universe, that was m minus cardinality I2. But then what's the relation between cardinality I2 and cardinality I1? Cardinality I2 is just cardinality I1 plus 1, right? Because you just added one more revealed row. This says that, okay, so this is like x minus I1 divided by 2 to the, so I'll put it into two parts, m minus I times n, and then I get like, this I2 was a plus So I2 was I1 plus 1. So I'll get a minus n outside, right? So I'm just substituting I2 by this formula. So if I substitute by that, I would get a 2 to the m minus I1 times n part and a minus 2 to the minus n part, right? 2 to the minus n part, and then there is a 2 to the n minus tau. Yes. So if you simplify all of this, so you get that this is just x minus I1 2 to the tau with respect to its universe, m minus I1 times n. So I'm just saying that this 2 to the n, so let me just say this 2 to the minus n, 2 to the n minus t, the n and n would cancel out, so you'll only get a 2 to the minus t. Sorry, it should be a 2 to the minus t. Yeah. Are there any questions? We didn't do anything super crazy. What did we do? We know that I2 is just I1 plus 1 because we added one row, so that's how the cardinality goes up, and we just expanded I2 by I1 plus 1. So this I1 plus 1 is inside a minus sign, so that plus 1 becomes a minus 1, and then it gets multiplied by an n. So it's like it, so you get a 2 to the minus n factor out, and then this is the earlier. So if you, so what did we achieve? So this is the earlier invariance ratio times 2 to the minus t in the bottom. Yeah. So let me just rewrite this. So this is saying that to x minus I2 with respect to this universe, m minus cardinality I2 times n is at least, so 2 to the minus t at the bottom is like 2 to the t at the top, right? So it's 2 to the tau, not t, tau, sorry, 2 to the tau times x minus cardinality I1, so sorry, set I1 divided by 2 to the m minus I1 times n. But this was the ratio from the last time, right? This is the invariant at before the beginning of the while loop. So we know that this quantity is at least this much. So we know just by maintaining the invariant, this is at least this much. Yeah. So we can just plug in that. So by invariant at I1, we get that this is at least 2 to the tau divided by 2 to the minus t minus I1 times t. So this t would go inside this thing as like, so if you just expand this out, this is like minus t minus cardinality I1. This tau would go inside as a minus in height. So there's a minus here and a minus here that cancels out. That's a plus tau. So if you bring that tau inside, this is what happens. So you'd get 2 to the minus t plus I1 plus 1 tau. Yeah. But what is this? This is nothing but cardinality of I2. So we get that this is exactly 2 to the minus t minus cardinality I2 by tau. Okay, so we have proved the invariant. So this is the invariant. So hence we have proved invariant at I2. And this is what we wanted to do. I2 was the next step. Yeah. So we are done with this proof. So there were a bit of calculations involved, but most of them are straightforward. So there are two things to remember. One thing is like, how does tau come into picture? So tau says that tau is the threshold of information for a revealed row. It says that if you remove, so this was the most crucial thing that we used in all these calculations. So this was this step. Let me highlight it here with this cool blue. So this says that if you remove a revealed row, because a revealed, so by definition a revealed row is something where if you take the matrix where that row is absent, only that row is absent, the number of extensions into that row is at most 2 to the n minus tau. So if you remove the revealed row, you don't shrink the set of matrices by too much. In fact, you only shrink the set of matrices by at most 2 to the n minus tau factor. But this is equivalent to gaining tau bits of information. Although, so what is happening? Let's think about this process at initially. So initially we know that cardinality of x by 2 to the mn is at least 2 to the minus t. So we know this. We know that x doesn't leak too much information. So this is like saying t bits of info in x. And let's say 1 was a revealed row. So what is this saying? That is saying that if you take a typical matrix in X and you remove the first row and you look at partial matrices which are like this kind of partial matrices, the number of possibilities for filling in this row, the first row, number of possibilities of first row on average, obviously. So I'm looking at a typical matrix X, but not some worst case measure. So number of possibilities of first row that goes into x in x is strictly smaller than 2 to the n minus tau. So this says that if you remove the first row, you should at least you cannot shrink the set of matrices by more than a 2 to the n minus tau factor. Yeah, but we said that whenever we shrink a set by some factor 2 to the k, that's like revealing k bits of information, right? But remember that we always measured information with respect to the maximum possible, with respect to the universe that this object lives in. So by chucking out this first row, this set x minus 1 now lives in a smaller universe. So this is a subset of matrices where you don't have the first row, right? You don't have the first row, but you have all the n columns. So this lives in a much smaller universe. So in that smaller universe, you only have like 2 to the n 1 over 2 to the n possibility of the original set of matrices. So originally you had 2 to the mn matrices. In this universe there's only like, so this cardinality of this universe is nothing but 2 to the minus n times 2 to the mn. So you kind of lost n minus tau bits of information, but by looking at this restricted universe you gain another n bits of information. So your total gain is like, so the loss is n minus tau plus the gain by going into a smaller universe was this plus n. So that's like so the so the n and n cancels out. So that's like tau bits of information. So this says that you have accounted for tau bits of information outside the rows 2 to the m, 2 to m. And this is what the invariant is saying. I did say this intuitively at the beginning, right? So what did the invariant say? The invariant is saying the invariant is saying that every time you identify a revealed row, it accounts for tau bits of information. So this is the number of revealed rows, this is the amount of information revealed. And this cannot be so the maximum amount of information is in the matrix is T. So after I rows, at least an I tau part of that information should be taken away from the total amount. Yeah, this is the invariant. So if you ever forget this invariant, remember this intuition. So here the intuition is more important than the actual technical details. Hopefully you can recreate the technical details fairly easily. It's just this kind of potential argument where you have this kind of pruning algorithm which prunes your set until you cannot find a revealed row, and then it stops. And then you prove this invariant that every step of this pruning algorithm, you're identifying a row and identifying tau bits of information that are in that row. So if you project that row away, you will have t minus tau bits of t minus like I tau bits of information in the matrix. So yeah, So are there any questions about this whole calculation or any of the intuition that I explained? So I'm deliberately trying to be slow here because this is like the crux, the main proof techniques that goes into many of these composition arguments, this kind of potential arguments, and we would see this in the F composed universal relation lower bound as well. It's going to be very similar. Okay. Yeah, if there are no questions, so what did we end up proving? We ended up proving that the number of revealed rows is bounded by the communication by the threshold. Okay. So what do we do? So what is our process? So we have this set x pi. So remember we had this set x pi. The cardinality of this x pi was at least 2 to the minus t times 2 to the mn. So this is a set satisfying these things. What was the t here? So t was the amount of communication, so that we set to be m minus order square root m. So t was m minus something like 4 square root m. And then we run this pruning algorithm and identify the revealed rows. So for that I need to set the threshold. So if you could do this calculation on your own, and you can find out that the best kind of threshold that works out for us is something like square root m. This might seem a bit mystical, but here is the reason. So what is happening? So we know that, okay, a revealed row, so if we set the threshold to be tau, a revealed row would have more than tau bits of information. This is revealed. And in an unrevealed row, there could be still like tau bits of information. We can't say that it has no information. There could be like exactly tau bits of information. It's not more than tau bits of information. So and we know that in the second stage we can, using some kind of trick, we can force the players to solve the universal relation on an unrevealed row. So they have to find a difference in an unrevealed row. But if they already know tau bits, what's the length of this row? This is n bits, right? So there are only n bits in this row, and in the first stage, by this argument, whatever we argue, it's only going to say that they are not sure about at most at least n minus tau bits. So maybe they know about these tau bits, so they only, we can only for sure say that they don't know about the remaining n minus tau bits. So the best kind of lower bound that you can prove for the second stage is something like n minus tau. So if you choose a first stage of m minus 4 square root m, whatever that is, and then you choose a threshold, the best that you can do here is like n minus tau. So we don't want tau to be too large. So maybe a good idea is to set tau to be constant, but there is another opposing constraint that comes on tau, where we want to say that tau cannot be too small either. So we'll see what that is. But if you like, so this constraint wants tau to be as small as possible, and we'll get another constraint which wants tau to be as large as possible. So the middle ground is something like, so this kind of some kind of product of two things, and the middle ground is at the square root. So you want to optimize something like x square being m, x square root m is the thing. So one of these constraints is that the kind of lower bound that we can prove for the second stage, that demands tau to be as small as possible. So the other thing that we'll see in a few minutes, what's the other opposing thing. But so we are going to set tau to be square root m. So the number of revealed rows is going to be something like m minus m over square root m. Okay. So theorem 1 says that there are at most number of revealed rows is less than m minus square root m divided by square root m. So the number of revealed rows is something like square root m. So yeah, that's the other constraint. So the number we don't want number of revealed rows to be too large either. So we get this to be square root m, so nice and good. But here is the problem. So what did we want? So we wanted to ensure that in second stage players can't find a difference in the inner revealed row. And we said that we can ensure this as long as for all revealed rows I in I, if we set AI equal to PI. Okay, how do we do this? This is somewhat tricky. There are two ways to do this. So one way is to like modify this pruning algorithm. So remember this pruning algorithm that we had the set x pi. We run this pruning algorithm on set x pi to identify the revealed rows. But whenever we identify a revealed row, we want to set AI equal to PI. Okay. So how do we do that? So far we have been only looking at the set of matrices, but remember that for every matrix in the set x pi, there's also a set of column vectors. Okay. So we want to do this. So how are we going to do this? We use this pruning algorithm, but okay, so I'm going to minimize this as much as possible. Yes. And then we will not just do this, we will do something more. So we'll add I to I union j. So whenever we find a revealed row, I hope this is still readable, please let me know otherwise. So we add an I to the ij, and then we want to make sure that for the set of matrices that we have, and we have a bunch of vectors associated with it, we set AI equal to PI. Okay. So let me, like, before I describe it in the algorithm, let me do it with an example where I assume that x is set to be x pi, x is a set of m by n matrices, and our algorithm identified that one is a revealed row. So this says that so if you look at x minus 1 versus x1, an average degree of a node here is strictly smaller than 2 to the n minus tau, right? So this is a definition of 1 being a revealed row. So if you look at the set and view it as a bipartite graph, the left average degree is quite low. So now what we're going to do is that we will so in the pruning algorithm, we are only going to think of the set x minus 1. So we want to just think of this set x minus 1, but remember that the set of vectors that are associated is for full matrices, not partial matrices. So I want to somehow like say that these are the set of vectors associated with a partial matrix in x1. So what do I do? So I don't care about how many extensions I have to the first row. I only want so what do I want? After finding the revealed row, I'm going to focus on this set, right? X minus 1. So I want to keep the set of matrices to be something so that if you project away the first row, I still get x minus 1. So I'm going to remove certain things and I'm going to keep something. So for every node here, maybe there are like multiple edges that go out of this. So I delete all the other edges. So I modified this. So I'll keep, while I maintain set x, I'll also maintain a set, let me call this x dash. So I obtain x dash as follows. Initially x and x dash are the same, and I look at the graph. So identify a revealed row. So here it is row 1. So after I identify row 1, I remove for every node on the left, I remove the edges out of that node except for one edge. So I keep one edge alive. So let me put that in green. So I keep one edge alive and I remove all the other ones. So this is like, so if you think about, like, let's take a sample example. This is like, here I have this partial matrix 0 0 1 1. So maybe I've removed the first row, so maybe first row can be 1 1, or it could be 1 0, or it could be 0 1. So what I'm saying is that my set X had all of these three things, right? My set X had 0 1 0 0 0 1 1 0 0 0 0 1. So it had three of these matrices and 1 1 0 0 0 1. But I want to just focus on the set X minus 1. So I want a subset of X where every partial matrix in X minus 1 has a unique projection onto that subset. But I don't want to lose anything in X minus 1. So what am I going to do? So I'm going to remove these two things. So to get X dash, I'm going to remove this one and this one. I don't care which two. Like if there are 3, I'll remove 2. If there are 5, I'll remove 4, and so forth. And I'll just keep this node in X dash. So how do I, so is this clear to you? So if I have a revealed row and I have currently a set of set X dash, set X, I choose X dash by choosing one of the neighbors. So if I have like many neighbors for a matrix in X minus 1, I'll just choose one of them. So now note that even for this X dash, so it's the case that if you look at X minus 1 versus X dash minus 1, they are the same set, right? You did not lose any partial matrix from X minus 1 because like there was a representative in X dash. So it's like, so we know that first row is a revealed row. We don't care what we are going to fill in for that row. So we're going to check out, if there are like 100 extensions, we are going to check out 99 extensions and only think about one extension. So this reduces the set of matrices that we have, but it does not reduce the cardinality of the set of partial matrices that we get by removing this revealed row. But because we kept at least exactly one representative for every partial matrix, right? So now I can think of the A axis associated with X dash as well. So so every X in, so X dash is a subset of, so I didn't define it formally, but X dash is a subset of X, and for every X in X, so for all X in X, there were this bunch of vectors associated with this matrix X. So we can keep the same subset of vectors with X dash as well. Yeah. So the formal way to define this set X dash would be that we would choose this extension function. So this is going to be, we're going to assume that, so we have removed the revealed rows, right? So need some more space here. There's this extension function which takes a partial. So this is extension function EI. So this is an extension function. It's a function, so it takes one object and produces another object. It takes a partial matrix of the form X minus I. So X minus I is not a full matrix. It doesn't have the rows indexed by I, and it produces a full matrix. It produces, so initially, what is this EI? EI is initially, it's initialized to be the identity map. EI for I equal to phi, X minus I is just X, it just produces the X. But it's interesting when once you identify a revealed row. So for example, here EI is described by this arbitrary choice of the extension that we pick. So for example, I'd say that if this is my X dash, so what is E1 of this partial matrix? So E1 of this partial matrix 0 0 0 1 is just this matrix where I choose to fill in 1 1. So for every vertex I associated this one unique neighbor on the right side, so that's going to be the extension. So 1 1 0 0 0 1. And I can describe the extension function for the entire set by choosing one such green edge. But you might ask, there are many, like, why did I choose 1 1 to be the green edge? No particular reason. You can choose any one of them. You can arbitrarily choose one of the neighbors, but you have to choose exactly one neighbor. It's not too important which neighbor you choose. Yeah. Are there any questions about the extension function? There's just some technicality to, like, so if you remember the set of vectors or the set of inputs that we give to a player, we can't give partial matrices. We have to give them full matrices. So this is one way to like extend partial matrices that we are thinking about into a full matrix. Yeah. So what are we going to do? So we are going to once now we need to modify the while loop a bit. So once we identify a revealed row, we are going to think of this set x dash. Oh, I need to also maintain a set x dash. So initially there is this x dash, which is initially set to be x. Yes. And what are we going to do? We are going to do the following. For this, so we have identified the jth row as revealed row in this iteration, and we're going to remove that row. So for every partial matrix in x minus I union j, so for every partial matrix in x minus, so for all, let me call this, so for all, maybe let's not call it x, let's call it z in x minus I, x minus I union j. So these are the partial matrices where the set I and the row j are removed. We would choose one of its neighbors. So the z might have had many neighbors onto xj, right? So we're going to choose a neighbor that is like just arbitrarily choose one of the neighbors. Yeah, we'll choose just one neighbor. So we will, for every such thing, we'll identify one particular thing, and we'll say that E of z, so E of z of that, let me call this ej. Ej of z is just z concatenated with xj. So I find, so for every partial matrix z, I find one extension onto the row j. So remember that row j is a revealed row. There could be many extensions. We choose some particular extension, arbitrary but exactly one extension, and we call this so this z composition xj means the matrix obtained by putting xj into the row j and into row j. So this function completes this partial matrix onto the jth row as follows. So for every z in here, we would identify one neighbor from xj. So this is from, so where is this from? This is from the graph x minus I union j versus x minus j. And what are the edges? The edges are x minus I. So we are looking at the set x minus I, and we have identified j as the revealed row, and there's this neighborhood graph. For every such z which is on the left side, we choose one unique neighbor, and we define the jth extension function as that completing this partial matrix into another partial matrix where we add one more. So let me just write this, define ej as here. So now if you think about it, ej takes you from a partial matrix where rows indexed by capital I and small j are missing, but ej takes you to a partial matrix where row j is added back, and now we have an extension to take from partial matrices where all of row I is missing. We are inductively building this. So we set the new ei union j to be just the earlier ei. So I should do this before the update. So this would be confusing. Okay. So I do this here. So I define this. So let me just add that back later. So this e extension function to take you to a complete matrix including row j is just first apply the, sorry, that's the wrong color. So first apply EJ on a partial matrix from X I union minus I union J, and then apply the function I so that you get it this way. So basically, like, yeah, so we have defined a unique way to go from partial matrices in X minus I to M by N matrices. And now we need a way to go from partial matrices which not only have the rows indexed by I missing, but also have the row J missing. So we first say how to fill in row J, and then we can use this earlier inductive thing which we have built, which is EI, to go into a full matrix. Yes. And then you do the natural thing, which was I had here, and then you update I to be I union J. Yes. So far we okay. So I think I'm out of time here. Uh, Maybe it's a good time to pause, and we can continue in the next lecture. So I realize that I'll also have to rearrange the lecture plan a bit. So we are still with the composition of universal relations. It's taken somewhat longer than what I thought. So I'll do some, but because I've explained so many things, composing the proving the lower bound for composition of a function with universal relation is going to take much less time. So I'm going to swap that in for next week, as well as completing this argument, and uh, we'll do the switch. Yeah, I guess. So just to summarize, what did we see? We found a way to identify revealed rows, but now what we are trying to do is, like, we are trying to fix the AI, the vectors, the corresponding value in the vectors to be the same for both Alice and Bob. So we didn't do much. What we did was, like in the earlier pruning algorithm, we added a way to go back from partial matrices to full matrices, and we're going to use this map to do something. Yeah, I guess I'll stop here and stick around if there are any questions.